Hello and thanks for watching. In this video we're going to define an n-dimensional real space. We're going to loosely define what a vector is, and then we're going to talk about its axioms. Okay, so first off, you want to say that this Rn is just this set of vectors, which I'm going to denote as an underlined v, because I cannot really produce a bold letter. However, in text you may see a bold letter representing vectors instead. Okay, so we have an underlined v, which is a vector, equal to some v1, v2, and so on up to vn, such that we have v1, v2, and so on up to vn be real numbers. Oh. Okay, so as you can see, this n-dimensional real space, which we'll just call Rn, is the set of vectors such that all of its elements are real. So what is a vector? We may be used to the traditional sense of just saying a vector is something which has direction and magnitude, but for now I think it's better to think of a vector as just a point in space, or rather elements of a set. So this Rn is just the set of vectors with real components, and a vector is just a point in space. So it seems quite pointless to define this, but as we go along in this linear algebra course, we will realize that vectors have some really nice properties which we can use for different things. So this set is a set such that we can add together elements, and we can multiply by a scalar. We can also multiply by other vectors in a sense. However, these products are defined in different ways, which we'll cover in a different video. So firstly, I will say that for any v and w in Rn, we have that if the vector v is equal to this, and if the vector w is equal to w1 and so on to wn, then we have the vectors v plus the vector w is equal to w1 plus w2, oh, not w2, w1 plus v1 and so on, vn plus wn and so on. So we just add them component wise. We add the first row to the first row, we add the second row to the second row, third row to the third row, nth row to the nth row. Okay, and this kind of what if we tried to add like two vectors which are not in the same set? So say we had like a v in R2 and we had a w in R3. So if we had this, we'd have like v equal to v1, v2, and we'd have w equal to w1, w2, w3. Now if we tried to add them component wise, this doesn't really make any sense, because would we add the v1 to the first element, or would we add it to the second element? We don't know. They're not the same, I suppose loosely in a sense, they're not the same dimension. So we can't really perform this addition. So we require the vectors to be in the same space for us to add them together. Okay. And now we're going to define some axioms for this vector addition. So firstly, for any vector v in Rn, actually, sorry, for any vector v u and w in Rn, we have that firstly, we have that there is an additive inverse. So what this means is that we always have some negative or some value such that we have v plus some other vector, which we'll call minus v, equal to the identity. So this identity is just some value such that when we use it, it just makes everything remain the same. So defining it properly, we say that the second axiom, existence of the additive identity, we say that we have v plus this I equal to I plus our v, which is equal to v. So this identity is saying that basically, no matter how we look at it, it does not change our vector. And in our n-dimensional real space, in our Rn, this additive identity is just 0, well, the 0 vector, which is just a vector with all of its elements being 0. So to see that this is true, if we take a general vector and add it to the 0 vector, we just get v1, v2, and so on to vn plus 0, plus 0, plus 0, and clearly when we add a real number to 0, we just get the same real number back. And so you can kind of intuitively see why the additive identity is just 0. Okay, and now similarly, when we go back to the additive inverse, if we put 0 back here, then we see that if we have some vector, v1 to vn, and we add negative v1 and to negative vn, we just get a vector full of zeros. Okay, so now quickly to define, or no, moving on to our next axiom, we have that addition is commutative. So what this means that for v plus the vector w, this is equal to the vector w plus v, and I feel like I don't really need to prove this. However, the viewer is welcome to. Most of these follow from the fact that real numbers themselves are, for example, commutative, or they have an additive identity, or they have an additive inverse. And additionally, the associative, one second. So we have that v plus w plus u is the same as v plus w plus u. Okay. These are our axioms for vector addition, and they basically just follow from the axioms for addition in real numbers. So to define scalar multiplication, now this is also very, very similar to our real numbers themselves. So now we'll say that if we have some vector v equal to, well, if we have some vector v in Rn, so we have this vector here with n elements, we say that for some lambda, where lambda is a real value, we have that lambda multiplied by v is equal to lambda v1 and so on up to lambda vn. So what we're saying is that if we multiply by some scalar constant on the outside, this is the same as multiplying each component individually by the same scalar value. So now to define the axioms for scalar multiplication, we firstly say that the first one is multiplication by 0. So we say that for any so if we have some I'll just write those here. So here I'm just saying that v, w and u are in Rn, and these two variables, lambda and mu, are real values. So if we have some lambda multiplied by a vector v, if this is equal to, well, the 0 vector, then we have lambda equals 0, or we have that this vector is equal to the 0 vector. So what we're saying is that if lambda is 0, then no matter what vector we have, this is equal to the 0 vector, which intuitively should be true, because when we defined our scalar multiplication here, we're multiplying every component by 0. Okay, so our next axiom is multiplication by 1. By 1. So suppose we have 1 multiplied by some vector v. This is just equal to the vector itself, which again makes sense, because if every lambda value is 1, we just get the same thing back. Third axiom is that we have associativity for scalar constants. So if we have lambda times mu times a vector, this is the same as having lambda multiplied by mu times our vector. Again, this is kind of intuitive, because of our axioms for real numbers. So associativity, and then our fourth axiom is distributivity, and this kind of links our scalar multiplication with addition. So if we have some lambda multiplied by these vectors added together, this is the same as having lambda times the vector v plus lambda times the vector w. Okay, so now you might be wondering, okay, why did I label these as identities and inverses, but then I didn't do the same thing for multiplication? Well, it's because this additive identity does not exist, neither does the additive inverse in most cases. Okay, this is because consider the zero vector, or rather consider lambda equals 0. If we have lambda equal to 0, we cannot find another vector or another scalar to bring back the vector to its original point, because when we multiply 0 by anything, we just get 0. So we cannot transform the vector back to what it originally was. Hence, 0 would not have an inverse. And so if there's no inverse, then there can't be an identity. Okay, that's all. Thanks for watching. Bye bye.